Imagine a glorious future where humans have overcome our present troubles, and we eventually leave this tiny planet behind to live among the stars. In time, our descendants span the entire Milky Way, countless trillions living in harmony from the galactic center to the most distant spiral arm. One day, a message arrives from outside, from another distant galaxy, another distant cluster. There is other life, other intelligence out there in the universe. Ideas are exchanged and science, art, and philosophy prosper. And eventually, plans are made. In the darkness of intergalactic space, the two great civilizations will meet. Many generations labor to build the immense craft capable of traversing great distances, and many generations are born, live, and die on the immense journey. But after countless millennia in the inky blackness, the emissaries of the two civilizations approach. Two individuals float across the void, hands reaching out. They touch, and both vanish in a blinding flash. The great ships stand off from each other, staring in amazement. The civilizations are fundamentally different, and it is only now it becomes clear. One is made of matter, and the other antimatter, and any contact leads to annihilation. The ships retreat into the darkness, knowing that true contact will always be impossible. But how did it come to this? How did they not know about the difference in their fundamental makeup? They had shared their science, their mathematics, and their engineering. Surely, this difference would have been obvious. But the scientists knew better. They knew that nature holds onto its secrets tightly. They knew that written into the laws of the universe were rules that cloaked these secrets, rules fundamental to the functioning of reality. They knew that these rules were built into many of the universe's processes, from the supermassive to the microscopic. And they knew that it was these rules that had helped reality freeze in the first billionth of a second of time. And behind them all, they knew that there was always one common factor: symmetry. Two great civilizations inhabiting two distinct and distant regions of the universe, and yet we know their laws of physics must have been the same. Then how could they have failed to tell matter from antimatter? Two particles, two atoms, two intergalactic beings with opposite electric charge. In our patch of the universe, matter is everywhere and antimatter is rare. But in their patch of the universe, the inverse must have been true. Whilst we live by the light of a star, they lived by the light of anti-stars. Whilst our ships were built from atoms, theirs were constructed from anti-atoms. It would be understandable to think that the laws of physics do not care about the difference between matter and antimatter. But that is not quite true. We now know that nature does treat matter and antimatter slightly differently, though these differences are subtle and unexpected, and related to one of the deepest concepts in all of physics. What is symmetry? We all know our first perception of symmetry, a mirror reflection from left to right. Armed with such a mirror, a child can sketch a symmetrical shape, with what is on the left also seen on the right, and vice versa. But looking in a mirror reveals that this reflection runs deeply in nature. Our faces and bodies are symmetrical, a right eye with a left arm with a right. Nature makes many uses of this mirror or bilateral symmetry. Most mammals, reptiles, birds, and fish share this simple mirroring. And when the rules of nature's symmetry are broken, such as the oversized claw of a fiddler crab, the appearance can be quite jarring. But symmetry is more than just reflection. A starfish builds itself using rotational symmetry, so when rotated, its appearance does not change. A millipede uses translational symmetry, building its body with identical chunks. Through these symmetries, nature is being economical in design. Symmetry can also spark a deep emotional response. In human concepts of beauty, symmetry of appearance is pleasing, even though beauty is only skin deep and inside we can be quite asymmetrical. And this appreciation of symmetry has made its way into art and design. The great temples of the ancients in Egypt and Greece show exquisite symmetry, as do more modern buildings like the Taj Mahal and Arc de Triomphe, and many great artworks such as Da Vinci's Last Supper. And art and design call on more than just simple mirror symmetry, as rotational symmetry can be powerful. From the rotating discs of the pre-Columbian Americas to the exquisite Islamic patterns adorning many mosques across the globe. Indeed, the massive Pentagon, home to the US Department of Defense, bears its geometry in its name. Symmetry is everywhere. But you might be wondering how this relates to the fundamental rules of the universe. Well, our story starts, as all good stories do, with a duel. At dawn on the 30th of May 1832, two men met in a field outside of Paris. The cause of the conflagration is unclear, but rumour has it it was over the affections of a young woman. By the time the sun was fully up that day, 20-year-old mathematician Évariste Galois lay dying in the grass. The night before, Galois had had a premonition of his untimely death. Into the early hours, he had scribbled with letters to friends and colleagues, and amongst these missives, he had pulled out the last of his mathematical ideas. For in his short life, Galois had brought many new ideas to the world of maths, and central to these was the idea of symmetry. The mathematics of symmetry was not a new concept. Ancient geometers had realized that a rotated circle remained the same circle, and triangles, squares, and pentagons appeared the same after fixed rotations. But Galois saw deeper. His focus was algebra, and more specifically, polynomials. Polynomials are equations with quantities to a power, squares, cubes, and higher. For example, 1 plus x squared is a simple polynomial, as is 3 plus 5 times x to the power of 5 minus x to the power of 7. Such polynomials are found across all of science, engineering, economics, and many other fields. Other mathematicians had scrambled to try and find algebraic solutions to higher-order polynomials, but Galois wondered if such an equation existed for all polynomials, one equation to unlock them all. Yet instead of discovering this ultimate equation, he actually showed it was a fool's errand. The solutions just didn't exist. And he didn't do this by simply fighting through the algebra, but by looking into the symmetries of the solutions. He realized the solutions to polynomial equations were complex numbers, each being a point on the infinite complex plane. These points could appear as shapes, triangles, pentagons, or others. And shapes, of course, have symmetries. They can be reflected or rotated. This was a radical way of doing mathematics, translating equations into a geometric picture and thinking about their symmetries. And since this work in the early 19th century, mathematical insights into symmetries have grown. And it has since blossomed into group theory, the study of groups of things that share properties and symmetries. Modern cryptology is underpinned by group theory, but it is symmetry's impact on science which has been the most startling. And so, as he lay dying in the morning light, Galois couldn't have known that his scribbles would revolutionize our universe. Long before they met, our two great civilizations came into contact. Radio beams were fired across the universe, taking many millions of years to reach their destination. It was a slow and cumbersome way of talking, but this new conversation with our distant neighbors did at least work. Both civilizations knew the laws of electromagnetism. On Earth, the jiggling of atoms formed the radio beam that carried the messages. and in the instruments of the aliens, charges jiggled as the messages arrived. But unlike on Earth, these were anti-electrons, positrons, dancing to the beat of the radio waves. Electromagnetism has a fundamental symmetry. If you swap all the positive and negative charges, the outcomes remain the same. This meant that the exchange of radio waves alone between the two civilizations could never tell matter from antimatter. Something else was needed, some crack in the symmetry of physics. And to understand why, we need to start our story almost a century ago. We need to start with a funeral. On the 1st of May 1935, an obituary appeared in the New York Times. This was not unusual, but the author, famous physics professor Albert Einstein, certainly was. Emmy Noether, Einstein wrote, had been the most significant creative female mathematical genius produced so far, and her insights had been necessary for the deeper penetration into the laws of nature. But what did he mean? Emmy Noether was only 53 when cancer struck her, and while her name might not be as iconic today as Einstein and the other old fathers of physics, her work was just as important. And Noether's theorem has everything to do with symmetry. Key to this was one simple fact: the universe, nature itself, is lazy. With the coming of modern science, mathematics had steadily replaced mysticism, and geometric symmetries had emerged from the equations. The spherical pull of Newton's gravity resulted in spherical planets and stars, whilst the magnetic field of an electric current was found to be shaped like a cylinder. These geometric symmetries, symmetries of shape, were pleasing to the eye, but they were really only skin deep. There were other, much deeper symmetries lurking in the mathematics of the universe. As with any story, there were many potential players, but here we will focus on just two. The first was Italian-born Giuseppe Lodovico Lagrangia, better known as Joseph Louis Lagrange, and Irish mathematician William Rowan Hamilton. They share few similarities in their lives. Lagrangia lived through the French Revolution and was instrumental in bringing in the metric system, whereas Hamilton grew up as a wonder kid in Dublin almost a century later. But despite their separation in time, their work dovetailed on one key thing: reformulating the equations of Newton. And key to this insight was the idea that the universe was lazy, the curious concept of least action. Indeed, long before, the French mathematician Pierre de Fermat had proposed that light always took the quickest path through any optical system. Imagine you are at the beach, with waves crashing into the shore. Off in the distance, somewhere to the left, you spot something in the water. A person is waving. No, a person is drowning. You have to rush to save them. But which way do you go? You can run fast on the sand, or you can swim slower in the water. Dashing straight to the shore and then swimming out and left will take too long. Should you run along the shore and minimize the time you spend swimming? As you race the calculations in your head, you realize there is a better path, an optimal path. You can run partway along the beach and then dive into the water. This path will be the shortest time between you and the drowning man. All other paths are longer. Fermat realized that light traveling from one place to another is like you on the beach. Light takes the minimum time between 2 points. The bent path of light as it refracts in water is just like the bent path you take between the land and the sea. But of course, Fermat only considered this for light. Lagrangia and Hamilton wondered if this notion could be expanded across all of physics. And so, hidden within the equations, they found that all nature somehow always chose the laziest of options. This might sound strange. Why does the universe function like this? We still don't know, but it works. To test this, physicists define what is known as the action, and then consider every conceivable possibility of a physical process. Indeed, there are an infinite number of imaginary paths that light can take between 2 points, and for each of these paths, physicists can calculate the associated action. It seems that the path where the action is most minimized is always taken by nature. From Newton's mechanics and Maxwell's electromagnetism, from quantum mechanics to Einstein's general theory of relativity, the universe's laziness reigns supreme. And so the principle of least action is written in the language of mathematics. And it is this that Emmy Noether was looking at when she noticed something intriguing. She realized that if the equations possessed symmetries, then this would mean there would be special unchanging quantities associated with the symmetries. This was an idea central to modern physics. The idea of conserved quantities, amounts that do not change. Perhaps the most famous of these is the idea of conservation of energy. As schoolchildren, we are told that energy cannot be created or destroyed, only changed from one form into another. Throw a ball into the air and the energy you expend is converted into potential energy and then back into kinetic. Start a fire and the fuel you put in will equal the heat and light that comes out the other side. But that is just the beginning. Physics is full of conserved quantities. In particle reactions, for every positive electric charge that is created or destroyed, an equal but opposite negative charge is also created or destroyed. The total charge of the universe therefore remains a harmonious quantity of 0. In a collision between two objects, the quantity of momentum is conserved. The amount of momentum before the collision exactly matches that after the collision. And so in terms of momentum, the universe once again appears to be harmoniously balanced. But why are these quantities conserved? Other physical quantities, mass, speed, acceleration, temperature, are not. What makes these quantities special? What is it that separates the conserved from the non-conserved? The answer, as found by Emmy Noether, is symmetry. Imagine you have a physics experiment set up on a table, something involving springs and bouncing balls. You do your experiment and record the outcomes, how the various bits and bobs move and interact. Then you push the table 10 meters to the left and redo the experiment. Of course, moving the table does not change the outcome of the experiment. The springs stretch and the balls bounce in the same way as before. The physics controlling the experiment does not change with the change of location. And this means that the laws of physics have a symmetry, translational symmetry. To Noether, the existence of this symmetry had to mean that something was conserved, something didn't change. And from the mathematics underlying the principle of least action, the mathematics of a lazy universe, she showed that this conserved quantity is just linear momentum, meaning translational symmetry implied the conservation of linear momentum. And there were other symmetries hidden in the mathematics, meaning there must be other conserved quantities. Perhaps most startling is the implications of the symmetry in time. Performing the experiment tomorrow should give the same result as today, and it is the existence of this symmetry that results in the most famous conservation law. For symmetry in time results in the conservation of energy. Emmy Noether had found that the equations led to a remarkable conclusion, tested and proved countless times in the centuries since. Every conserved quantity in the universe can be traced to an underlying symmetry, and every symmetry results in a conserved quantity. Although they are not always straightforward. Many are buried deep in the equations of quantum mechanics, and whilst being subtle, their impact can be profound. In quantum mechanics, things are described by waves. These quantum waves are like ripples on a pond, but unlike rippling water, quantum waves are waves of probability. These waves share a lot of similarities with the oscillations of water. As well as a wavelength that tells you how long a wave is, quantum waves have amplitudes that tell you the strength of that wave. And like water waves, quantum waves also have a property known as their phase. The phase is a measurement of where in the cycles of oscillations the wave is. Is the wave in a peak or in a trough? but the properties of an electron are independent of the phase of its wave function. They don't change no matter how the phase may alter. And it is this symmetry, this similarity between the electrons that gives us the conservation of electric charge. Other symmetries in the mathematics of quantum mechanics reveal even more esoteric conservation laws. Baryon number, lepton number, isospin, and strangeness, to name a few. Symmetries can even be found that predict the fundamental forces. Gauge symmetries, for example, result in gauge bosons, like the gluons that hold protons and neutrons together through the strong nuclear force. The symmetry between protons and neutrons, their inherent similarity, results in this quantum force. And so when physicists unravel the complex interactions of particles in the Large Hadron Collider, these quantum conservation laws rule supreme. Inevitably, we should expect that all fundamental interactions are totally bound by these fundamental rules, symmetries and conservation laws operating hand in hand. Everything in balance. And indeed, they mostly are. But there are exceptions. And it is these exceptions that may have formed our universe. By the mid-20th century, astronomers were thinking about aliens. Giant radio telescopes scanned the skies for any faint beep from distant civilizations. Some wondered just what we would say to our ET cousins when we eventually made contact. But others worried about more fundamental questions. For example, the existence of antimatter beings. The problem was centered around telling left from right. This might seem trivial, but it is implicitly tied to matter and antimatter and the twin fates of our doomed intergalactic civilizations. How do you tell an alien the meaning of left and right? It's harder than you think. You can't send a picture, as they would need to know left from right to properly reconstruct the image. You can't refer to trappings of civilizations, such as writing, as they again would need a reference. You need to appeal to left and right written in the fundamental universe, and you need to find a break in symmetry that allows you to do this. You need to start thinking about parity. In 1956, the universe was broken. In a laboratory in Washington, D.C., individual atoms of cobalt were spinning in a magnetic field. The experimenter, Chen Ning Yang, was watching patiently for the cobalt to change, to undergo radioactive decay and spit out an electron. In cooling the cobalt atoms and placing them in a magnetic field, Wu could ensure that they were all spinning together, and she could chart the directions that electrons sped away from the cobalt. And conservation of angular momentum meant that they should be spat out from the poles of the cobalt, some heading from the cobalt north pole, and the same number emitted from the south. But as Wu sat and counted the electrons, a disturbing pattern appeared. Instead of a mix of electrons heading north and south, all appeared to be escaping from just one side of the cobalt atom. It appeared that this radioactive decay of cobalt was not symmetric. But what did this mean? So what if cobalt preferred to spit out electrons from one side rather than another? Well, it all came down to a concept called parity. Up until the 1950s, the conservation of parity was core to fundamental physics. It meant that whatever was seen in a mirror universe was as real as the physics that is seen in our universe. Think of an atom. When an electron jumps from one energy level to another, a photon of light is emitted. But in which direction does this photon flee? You should see half of the photons heading to the right, and the other half heading to the left. But what if you view the atoms in a mirror? The mirror switches left to right and vice versa, but it also flips spins from clockwise to anti-clockwise and anti-clockwise to clockwise. So the view in the mirror is half the photons moving to the left, half to the right. And so the emission of a photon, an electromagnetic interaction, obeys parity conservation. And the same is true for the gravitational force. Imagine a planet spinning and orbiting its star in a clockwise fashion. In the mirror universe, everything would slip to anti-clockwise motion. At the quantum level, there are other forces that we need to consider. Inside protons and neutrons, quarks interact with quarks, exchanging a small particle known as a gluon. This is the strong nuclear force in action, the force that binds your atomic nuclei together. Both electromagnetism and the strong force respect quantum symmetries and quantum conservation laws. Perfectly balanced. But there is another fundamental force, the weak nuclear force. And the weak nuclear force seems different. It is responsible for aspects of radioactivity, changing neutrons into protons and spitting out electrons. But radioactivity is not so common in the universe, and it can seem that the weak force is little more than a bit player. But it was this that all changed in 1955, when it was realized that the weak force is the strangest of them all. Particle physics had flourished in the first half of the 20th century. A flurry of particle discoveries and quantum insights peeled away the world of the very small. And as patterns and pictures began to emerge in the families of fundamental particles, the action of the weak force came steadily into focus. Chen Ning Yang and Tsung Dao Lee were at the forefront of this effort. As young scientists at Princeton, they began to explore what nuclear experiments had revealed. They knew that the weak force was responsible for some radioactivity, and that in these decays, the great Wolfgang Pauli had predicted the existence of a ghostly new particle, the neutrino. And whilst no one had ever seen a neutrino, the conservation of energy was sacrosanct, and so it must exist. Yang and Lee were puzzled, however, over what they saw. They understood that fundamental forces should conserve parity, but there was no smoking gun to prove that the weak force understood that this was the rule. And so an audacious idea took hold. Maybe the weak force didn't conserve parity. Maybe it wouldn't work in a mirror universe. Whilst this sounded interesting as a theoretical idea, they needed an experiment that could show that the weak force broke the universe. And this is why Wu had cooled her cobalt atoms and placed them in a magnetic field. Just like a photon being spat out of an atom, the spin of electrons can be switched between clockwise and anti-clockwise, and we should expect equal numbers of electrons heading both northwards and southwards. But of course, this was not what Wu saw in her sensitive experiment. Why would electrons preferentially emerge from one pole of a spinning cobalt nucleus? The startling conclusion was that Pauli's neutrino could only spin one way relative to its motion. This meant that there were only clockwise neutrinos, and by the conservation of angular momentum, they can only be emitted from one cobalt pole, the electron from the other. A mirror view of the neutrino would therefore appear to be spinning anti-clockwise, but such neutrinos simply do not exist in our universe. The mirror version of the weak force therefore also does not exist in our universe. The weak force violates parity. This discovery won Yang and Lee the Nobel Prize in 1957. It was one of the fastest ever awarded in physics, much faster than the 17 years that Einstein had to wait. Wu mysteriously missed out, but her name is written into the history books of science for the experiment that shook physics to its very core. The weak force violating parity means that neutrinos know right from left, that the universe itself somehow knows right from left. But the weak force goes deeper, and in the following years other forms of parity started to tumble, and it turned out there were other symmetries that the weak force liked to crack. And it is now that the mystery of matter and antimatter can begin to be unraveled. It was realized that order could be restored to the Wu experiment if, as well as parity, another transformation was made. If all the particles were transformed into their antiparticles, known as a charge conjugation transformation, the mirror view with the spin antineutrino could occur in our universe. This double transformation is known as CP for charge and parity. And so whilst the weak force violated parity, perhaps it would obey CP. But it didn't take long for a new series of experiments to show that this was also not the case. And this experiment explored the weird behavior of particles known as kaons. Kaons are mesons, a combination of one quark and one antiquark, and neutral kaons, kaons without charge, are a mix of a strange quark and a down quark. But there are two types of neutral kaons, one with a strange quark and anti-down quark, and another with an anti-strange and a down quark. This peculiar situation means that the two neutral kaons can mutate into one another, and a beam of neutral kaons has to be considered a quantum mechanical mix of the two. Kaons' lifetimes are very short, decaying into lighter mesons, pions, in about 1/1000th of a second, and the conservation of charge and parity together means that there should always be 3 pions in the decay. And so in 1964, an experiment was set up to explore whether the combination of charge and parity were actually conserved. Firing a beam of kaons down a long tube, physicists counted the outcome of decays. Almost all of the decays, 499 out of 500, resulted in a burst of 3 mesons, but 1 in 500 resulted in only 2 pions. And it was here the universe was broken once again. Charge and parity were not conserved in the decay of kaons. Once again, the result won the experimenters Val Fitch and James Cronin the 1980 Nobel Prize in Physics. But what does CP parity violation really mean for the universe? Deep down, it tells us that the laws of the universe are different for matter and for antimatter. Thinking back to the meeting of the great intergalactic civilizations when we began this journey, this finally gives us a solution to avert the disastrous events that unfolded. Neutral kaons must be considered a quantum mix of matter and antimatter, and sometimes this quantum mix can decay into electrons and its antimatter partner, the positron. If CP was conserved, these decays should produce equal numbers of electrons and positrons. But again, Cronin and Fitch found that CP was not conserved. For every 300 electrons produced in decays, there were 301 positrons. And so, all our intergalactic descendants needed to do was independently undertake experiments with neutral kaons, and they would have known matter from antimatter. They would have known whether it was safe to finally shake hands. Whilst communication through electromagnetism wouldn't help, nor discussions about gravity and the strong nuclear force, were this distant meeting to occur, we would be able to talk about experiments with the weak nuclear force. And there would we find absolutes. But the question remains, why does the universe break these seemingly obvious symmetries? It would be a much simpler place if the physics of matter and antimatter were perfectly symmetrical, perfectly balanced. And indeed, that is only the beginning. It seems the implications of CP violation, as it is known, have much more far-ranging consequences for the universe. And to truly understand this, we will need to return to the very beginning of time, when the intense fireball of the Big Bang somehow froze. What is the ultimate goal of fundamental physics? Is it to understand what everything is made of? To try and reveal the origins of the universe? To Einstein, on his deathbed, there was a simple answer. The ultimate prize was a theory of everything, a theory that would finally unite all of the fundamental forces. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Long the holy grail of quantum mechanics and general relativity, physicists have taken steady steps in this direction, first uniting the weak force with electromagnetism in the 1960s. The strong force took more work, but in quantum chromodynamics, it too joined the party. And the ultimate aim, the focus of fundamental physics for more than a century, has been to incorporate gravity, a goal that physicists have yet to definitively accomplish. But just how do physicists build these theories of everything? Once again, guiding them are ideas of perfection and symmetry. Important clues have come from high-energy experiments where particles are smashed together at high speeds. As the energies of the interactions are increased, something peculiar begins to happen to the fundamental forces. They begin to change their spots. They alter just how they operate between particles. They start to lose their distinct nature, and all begin to look the same. Let's consider electromagnetism and the weak force in the universe today. They seem radically different, with electromagnetism connecting charges and the weak force being a form of radioactivity. Electromagnetism is also carried by the massless photon, whereas the weak force uses three massive particles, the Z0 and W+, and minus. But at higher energies, this distinction begins to blur. In what is known as the electroweak theory, these seemingly distinct forces are truly one single force. And so, when the universe was hot and young, only this single force existed. It was the cooling of the universe through the Big Bang that broke their symmetry and made them distinct. At higher temperatures still, the distinction between electroweak and the strong force fades away, and it's thought that at ultra-high temperatures, gravity too becomes indistinct. This suggests that at the universe's birth, there was just one true force, the superforce, and this superforce was perfect and symmetrical. The Bible begins in Genesis with the line, "In the beginning was the Word, and the Word was with God, and the Word was God." The Bible begins with godly perfection that was ultimately corrupted. Modern cosmology begins in a very similar fashion. In the beginning, the universe was perfect and symmetrical. There existed the one true superforce, and it reigned over all. But this ultra-hot universe expanded and cooled, and fractures appeared in the perfect symmetry of the cosmos. Out of perfection, imperfections began to appear. The individual forces separated, first gravity, then the strong force. As the universe continued to cool, the weak force separated from electromagnetism. But these separations as the universe cooled were not uneventful. As a force went its own way, the very nature of the cosmos changed. The universe before and after the separation was distinctly different. It had undergone a phase transition. As temperature decreases, water freezes into ice. Its symmetry is reduced. In the same way, the separation of a fundamental force as the universe cooled marked a distinct fracture in the symmetry of the universe. Cosmologists think that these separations impacted the important features of reality. Gravity separating was at the Planck time, when the universe was about 10 to the power of minus 43 seconds old. This is an age of the universe we know almost nothing about, and until we can write down our grand unified theory uniting the quantum realm and gravity, it may forever remain a mystery. But the separation of the strong force is different. It occurred much later, at about the age of 10 to the power of minus 34 seconds. And this is a time that physicists think they have a much better handle on. For this is about the time that inflation blew up the universe. In the late 1970s, Alan Guth was worried about the cosmos. He had started his research career in particle physics, hunting for grand unified theories, as well as hunting for a permanent position as a professor. But in 1978, he attended a lecture that changed everything. The speaker was Robert Dicke, an elder statesman of science. Being at the other end of his career to Guth, Dicke had explored many mysteries of the cosmos, and in this talk he was wondering just why the universe appeared to be flat, rather than curved like a sphere or a saddle. Somehow, the birth of our universe must have been fine-tuned, selecting flatness from all possible geometries. Guth was intrigued by this seeming specialness of the universe and wondered if it related to the fact a chunk of the universe appeared to be missing. A chunk predicted, once again, by symmetry. The motivation was James Clerk Maxwell on the nature of electricity and magnetism. His equations were profoundly asymmetric, possessing electrical charges but no magnetic equivalent. All magnets we see have a north and south. Many before Guth had wondered where these magnetic monopoles, pure magnetic north or south poles, may be, and so Guth decided that they must be hiding. In the earliest moments of the universe, when it was hot and dense and seething, Guth suggested that the electromagnetism was symmetric and that magnetic monopoles were a part of the cosmic mix of particles. But as the universe underwent an immense burst of expansion, doubling 80 times almost instantly, the magnetic monopoles were thinned out enough so that there was only one per observable universe. After this period, known as inflation, there wouldn't have been enough energy in the universe to create new magnetic monopoles. They were effectively lost, never to be seen in a physics laboratory. So what happened to the universe during its dramatic expansion? A background field of energy known as the inflaton must have dominated. The density of the universe fell precipitously as all particles were robbed of their energy, and the universe became a frozen, empty place. But space still seethed as the inflaton eventually decayed and inflation came to an end. And so the energy of inflation was dumped back into the universe, reheating the universe to many billions of degrees and creating the matter that inhabits the universe today. But the magnetic monopoles were long gone. But there was something strange in the timing. All this started around the same time as a phase transition, just as the strong force separated. Was this just a coincidence? Or was it the departure of the strong force that seeded the inflaton with energy? We are still not sure. Indeed, our knowledge of the physics of this epoch is still a little hazy in parts, and so we cannot be sure that we have found the true culprit of inflation. Indeed, some have also tied the inflaton to the formation of the Higgs field, the field that gives particles mass, whilst others have wondered if the inflaton is just an early incarnation of today's dark energy. And so when the universe was about 10 to the power of minus 12 seconds old and a balmy 10 to the power of 15 Kelvin, all of the fundamental forces had separated into the distinct forms we know today. But the action of symmetry breaking still had one more trick to play, for it was in this epoch that baryogenesis occurred. This is the time when the superfundamental particles, quarks and gluons, began to condense into protons and neutrons, and the matter in the present universe, the matter of you and me, was finally born. But a problem of symmetry remained. Remember that the energy of the inflaton was poured back into the universe after inflation, and this is the ultimate source of matter and photons in the cosmos today. This reheating should have equally produced matter and antimatter. One of the starkest asymmetries in the universe today is the odd preponderance of matter over antimatter. Cosmic searches have revealed a wealth of matter across the cosmos and the barest traces of antimatter. As an example, scientists believe there is about 1 part of antimatter to a quadrillion parts of normal matter within the Milky Way. So where did this asymmetry arise in the lifetime of the universe? Why is there so much more matter? It is thought the answer is buried deep somewhere in baryogenesis. Whilst we know and have seen that the laws of physics can differentiate between matter and antimatter, the degree of difference is simply too small to account for the difference in matter over antimatter, and so that still leaves us scratching at the fundamental laws of the universe to determine why there is any matter at all. We can also estimate the degree of matter-antimatter asymmetry from an unlikely source, the cosmic microwave background. These photons were emitted when the matter and antimatter in the universe finally annihilated, and for every proton or neutron in the universe today, there are about 1 billion of these cosmic microwave background photons. This means that the universe must have been almost symmetrical. For every billion antimatter particles, there must have been 1,000,000,001 matter particles. And it is this tiny difference that is the source of all the universe's mass today. It is sobering to think that we are only here because of this tiny asymmetry. But there is still one final mystery that symmetry could help reveal. If symmetry is our true guide, and fundamental physics is purely symmetrical, there should be more than just magnetic monopoles out there to be discovered in the cosmos. Within a supersymmetric theory, for example, for every quark there should be a symmetric squark, and for every electron, a supersymmetric selectron. This naming process carries on throughout the Standard Model, from neutrinos to smuons for fermions, and Higgsinos to photinos for bosons. A hidden supersymmetric universe of sparticles would be lingering just out of reach. Indeed, supersymmetry is a key part of many potential theories of everything, and scientists had long expected to finally find evidence in the Large Hadron Collider. But hunts for these mysterious particles in our colliders have so far yielded none of these supersymmetric candidates. All we find are the usual suspects, the quarks and electrons of our universe. Some physicists have claimed symmetry has led us astray and we are on the wrong path, but for others, symmetry is simply too alluring, and the hunt for supersymmetry and the superforce continues. We are almost at the end of our journey, and we have seen that symmetry is clearly central to our understanding of the universe. But it is really the breaking of symmetries that gives the universe its peculiar personalities. The fundamental laws and the existence of matter truly arise from cracks in perfection. But there is one final thing to consider. Even though it feels like the breaking of symmetries is something that happened in the distant past, our universe is still expanding, still cooling, still changing, and we are mere footsteps into the infinite future that lies ahead. And so, hidden in energies well below our experimental reach might yet be other, undiscovered symmetries. And as the universe continues to cool, one day these too might crack, fracture, and break, unleashing new forces and new phases that could radically change the cosmos. Our universe's march from perfection to ultimate corruption might not yet be over. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.